Hi, this is presentation 7 for ENGI 460. My name is Selassie Dumeno, and my partner is Andres Cordova. Brief overview, so we're going to be looking at four main things here. We're going to be looking at the Poisson process, and then we're going to look at some time-dependent Poisson process, and then the Poisson process in the plane, and then finally we're going to look at Markov chain, and then look at both the discrete time Markov chain and the continuous time Markov chain. Okay, so for the Poisson process. Poisson process is basically the occurrence of certain events that appear to happen at a certain rate, but completely at random. And they usually have the following properties, which is that they have independent increments, and then arrival times that happen in a small window can be or may be neglected, and then they also tend to have stationary increments. The equation you see to the bottom right of your screen is basically Pn of t equals e exponent negative lambda t times lambda times t raised to the power n over n factorial. And this is basically the formula for the Poisson distribution, basically. Alright, so next we're going to talk about the time-dependent Poisson process. Then this process is the important generalization, basically, of the simple Poisson process in the previous slide. And then with this process, the small case lambda is replaced by a non-negative function, lambda of t. And then the solution for this is basically obtained by capital lambda of t is lambda u du, basically from 0 to t. And one thing we have to note that lambda prime of t, big lambda or capital lambda prime of t, should be equal to lambda of t. And that can be verified by the formula below, which is basically your Pn of t is equal to the exponent of negative lowercase lambda times t, open bracket, capital lambda of t, bracket close, exponent n, over n factorial. Alright, so if we talk about a Poisson process in a plane, the scenario will be if we consider a two-dimensional domain for which C and E are both parts of that domain, but the intersection of C and E will equal an empty set. Basically, we can think of lambda as being the density of 2 points that is expected. That is the expected number of points per unit area. And the formula below basically represents it's basically saying that if P of 0 points in the region of area X, then the equation will be E raised to negative lambda times X. And then the second equation there is basically independent. So therefore, if pi r squared I minus 1 are independently distributed as negative exponentials with a mean of lambda minus 1, for example, the equation that we can apply to that would basically be minus 1 over lambda ln u of I. Now on to our Markov chain. We're going to start with the discrete time Markov chain. So let's say x of n is the state of the nth step in a homogeneous discrete time. with a discrete state Markov chain with state space S and probability transition matrix of P. Now, if we know that our x sub n minus 1 is equal to I, and that given a random number, the inversion of the cumulative distribution function may be used to obtain x sub n, which is equal to the min of the random number less than the sum of p sub I comma k. Now, we know that if the proportions of transitions are large, that formula tends to be inefficient. And in such cases, a better method will be to identify the lead change of state. And for that, we can use the equation below, whereby we can let the state immediately after the k event be x exponent k, and let m exponent k denote the number of steps between k minus 1 and in the k event. And therefore, using that inversion of the CDF, we can yield m exponent k, which will be equal to 1 plus ln r k over ln p I sub I. And on the other hand, we have the continuous time Markov chain, and that considers a discrete state with the same state space and a stationary infinitesimal generator Q. So what that equation will look like is that P of x parentheses t plus h will basically be equal to j bar x of t, and that will be equal to I close bracket, and basically that will all be equal to q sub ij h plus O of h. And we say that j is not equal to I, where qij is equal to 0 for all I in that state space. And then the simulation method used here is analogous to that described for discrete time Markov chain. So if we let t sub k be the time of the kth event, which is a state change, and then we let x parentheses tk minus 1 be the state immediately after the k minus 1 event, and given that x parentheses tk minus 1 is equal to I, and then t sub k minus 1 is equal to lowercase t k minus 1, it can be found that tk minus our tk minus 1 is exponentially distributed with the mean of negative q sub ii, and therefore our tk minus tk minus 1 will be equal to our ln r sub k over q ii, where rk is u 0 to 1. Now if we're given that our x of tk minus 1 is equal to I, then the conditional probability that the next state is negative qij over qii, and therefore given another random number uk, it's a member of u 0, 1, and that formula will be x of t sub k, which is equal to the min of negative qii uk less than the sum of q sub im. So I guess basically a big difference you can argue between the continuous and then the discrete is that with the discrete there is a transition matrix, whereas with the continuous we have a stationary infinitesimal generator.